Next we come to solvate isomers. Solvate isomers are the coordination complexes. They have the same molecular formula, but what is different is the number of the solvent molecules which is present as free solvent and as ligand. As an example, we have chromium H2O whole 6 Cl3. Now here all of the 6 H2Os are present as ligands. They are not present as free solvents. So if I take this and react it with concentrated H2SO4. Now concentrated H2SO4 is what? It's a very strong dehydrating agent. But if I react it with concentrated H2SO4, it will not lose water. Molecule will not lose water. But if I take this molecule and react it with AgNO3, then we will get 3 moles of AgCl will be precipitated. That is 1 mole of this complex will give 3 moles of AgCl. Now if I take Cr, Cl, H2O whole 5, Cl2 dot H2O. Now these both are what? These both are solvate isomers of each other. In the second one, 5 of the H2 are present as ligands, but 1 H2O is present as a free solvent. If I react this with concentrated H2SO4, it will lose 1 molecule of water. And with AgNO3, will give 3 moles of AgCl. So these both are solvate isomers. You can further try to make more solvate isomers of this. We can say that we have Cr, Cl2, H2O whole 4, Cl dot 2H2O. So this is also a solvate isomer of the other two. This molecule is going to lose 2 molecules of water if we on reaction with concentrated H2SO4, and it is going to give 1 mole of AgCl on reaction with AgNO3. So all of these are solvate isomers. Next is coordination isomerism. When there is an interchange of ligands between the cationic and anionic entities present together in a complex, it is known as coordination isomerism. So in coordination isomerism, the main thing is that both of your anion as well as your cation should be a complex. So we have done examples of those. In that, coordination isomerism can occur. This is the cationic entity. This is the anionic entity. Okay, and if there is an exchange of ligands between the cationic and the anionic entity, then it will be coordination isomers. So this coordination isomer will be CO CN6 Cr NH3 whole 6. So that will be its coordination isomer. And it does not mean that the entire ligands have to be rearranged or replaced or interchanged. If I take PTNH3 whole 4 and PTCl4, this we have already done, then I just exchange one ligand. Okay, on exchange of one ligand we get PTNH3 whole thrice Cl and PTNH3 Cl. This is also a coordination isomer. Basically what I mean to say, it's not necessary to take the entire ligand and exchange it. You can exchange 1 or 2 ligands also, and that will also classify as coordination isomerism. So the next and the last type of isomerism in structural isomerism is coordination position isomerism. So coordination position isomerism arises in those complexes in which bridging takes place, and it arises from the exchange of ligands between the two metal ions. Like this is a bridging complex. So its coordination position isomerism is going to be that's CO, then we have an NH3, and then we have a Cl. So you see that the exchange of the ligands take place between the metals. Here there was 4 Cl and here there were 4 NH3. Now in the coordination position isomer, what has happened, one of the Cl from this has moved towards this cobalt atom, and one of the NH3 from this cobalt atom has moved towards this cobalt atom. So similarly, more coordination position isomers can arise from this, that is, 2 of the chlorine atoms can move to this side and 2 of the NH3 can move towards this side, 3 of the chlorine can move from this side and 3 of the NH3s can move from this side. So there will be many more coordination position isomer of the same complex. So this was the last of our structural isomers, isomerism. So next we are going to see some questions upon structural isomerisms and how to identify whether a complex, which complex has which isomerism.